Okay, so in this lecture, we're going to look over a more general strategy for determining the convergence or divergence of a given series. The previous techniques that we've looked at have been somewhat specific to the terms of the series. For example, geometric series or the P-series test. With this test, we have a more general way of just determining convergence or divergence of a series. And this test is called the direct comparison test. So what does it say? It says that if 0 is strictly less than an, so an is going to be a positive term, which is less than or equal to bn, again, implying that bn is a positive term. So if that inequality holds for every natural number n, then we have two parts to the theorem, which are equivalent logically, and I'll get into that in a moment. So if the infinite series with terms bn converges, then the infinite series with terms an must also then converge. And the contrapositive of that statement is that if an, the infinite series with terms an diverges, then it must be the case that the infinite series with terms bn must also diverge. So why would this be the case? Let's look at the proof of this statement. Okay, so let's prove part one, and then we prove part one, then the contrapositive of that statement is equivalent logically will imply part two. So we're going to first let 0 be strictly less than an, which is at most bn, for all natural numbers n. And suppose the infinite series with terms bn converges. Right, to some number L. Maybe say that is this converges. Okay. So with that being said, note that L is going to be some positive number. Since each of the terms bn is strictly greater than 0, that sum of positive terms must be positive. So I would like to just note that. Note L is greater than 0. Okay. Next, let Sn, or maybe Sk, equal the kth partial sum of the an terms, and observe that the sequence S1, S2, dot, 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 SK, dot, 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 is a non-decreasing sequence and this is since each an is greater than 0. So when you're adding a bunch of positive terms, it's going to be getting larger and larger and larger, which is bounded above by what? Bounded above by L. So if we're always adding an, then the same, and an is less than or equal to bn, summing the an is always less than or equal to summing the bn. So taking bn to, as n goes to infinity, summing these terms, we get L. L is going to be greater than or equal to an. Now, bounded from above monotone increasing or non-decreasing sequences converge. So thus, limit as n converges. Implying that the infinite series an converges. Okay, so that proves part one. Why does that prove part two? Well, from logic, if P, then Q is logically equivalent to not Q implies not P. Okay. Not Q implies not P. So these are logically equivalent. So if Pn converges, then An converges is logically equivalent to if An does not converge, then Bn does not converge. And that's part two. So we're done. Okay. So let's look at an example. Of applying this theorem. Let's consider the infinite series. So from n is equal 1 to infinity of 1 over 2 plus 3n. Does this converge? Okay. Now the general strategy here is to look at bounding these terms from above and below as close as you can. And then for the ones below, you want to see if they diverge. For the ones above, you want to see if they converge. In this case, my first instinct is to look at maybe the geometric series. I see that the geometric series above converges with this note. So let's like look at the solution. So note that 1 over 2 plus 3n is less than 1 over 3n for all n, right? You're dividing by a larger number, so this is going to be at most this. And I should probably say like 0 less than that, at most that. These are all non-negative terms. So we have that part. So now let's look at, well, then if we look at the infinite series from n is equal 1 to infinity of 1 over 3n, well, this is the geometric series in disguise, right? This is just 1/3 to the power n converges since it is a geometric series with ratio r equal to 1/3. Now, since this series converges and this inequality holds, we know that that converges by the comparison test, the direct comparison test. So the series from 1 to infinity of 1 over 2 plus 3n converges by the direct comparison test. I should probably use capital direct comparison test. Yeah, that's the solution. Okay. So the trick is just determining the terms that you want to compare it to. That's the hardest part about this comparison test. But what you should really remember is that we have geometric series, we have p-series tests, we have the integral test, and you have something that won't satisfy any of those. You want to compare the terms of the series to something that you know how to deal with, basically. You want to compare it to a p-series, a geometric series, an alternating series, something, or not alternating, a telescoping series, things like that, where you can kind of get a handle on the convergence of the thing in question. Okay. So maybe let's look at another example. Probably shouldn't have erased that, but whatever. Let's look at, let's do another similar one. So it is equal 1 to infinity of 1 over 1 plus square root of n. Okay. Now, if we tried the same trick and looked at maybe 1 over root n, then what would happen? What would happen here? That you wouldn't get any information out of it, right? Because, like, if we compared 1 over 1 plus root n is at most 1 over root n. Now, if we looked at a series with that, we couldn't say anything using the direct comparison test because that would diverge. So if the larger terms have a series that diverges, and that doesn't give us any information. But what about if we look at something that's smaller, right? What about if we look at comparison, so note that 0 is less than 1 over n, which is less than 1 over 1 plus root n for all natural n. So then we have a harmonic series that diverges, which is less than this term. So then the harmonic series n equals 1 to infinity of 1 over n. So this is really, the harmonic series is like a p series of p equals 1. P equals 1, it diverges. Diverges by the p series test. Implying that the larger sum also diverges. Diverges by direct comparison test. Okay. So this is an example of from above and then from below. basically using part 1 and then using part 2 from the previous step here, the direct comparison here. Okay, what's the next theorem? Oh, limit comparison. So let's see. Chalk. So what does it say? So if an greater than 0, bn greater than 0, and the limit of what is it, bn over an over bn? Yeah, that's it. An over bn equals L, with L non-negative, or greater than 0 as your textbook uses, shouldn't matter in the long run. Then the sum is equal 1 to infinity of an, and the sum is equal 1 to infinity of bn. Either both diverge or both converge. All right, so limit comparison test. Now, I suppose I'll prove this one. Remember how it goes. So suppose the hypothesis, which is saying that an greater than 0, bn greater than 0, and the limit of an over bn equals L, which is greater than 0. Okay, so by definition of the limit, so we can use the epsilon delta definition of limits. So next, we choose epsilon equal to 1, and observe maybe. There is some natural number n greater than 0, such that n greater than or equal to capital N implies that the distance from an over bn to L is at most epsilon, which is equal to 1. Okay, that's just the definition of this thing converging to that thing. Right, so basically there's an index where when little n is big enough, bigger than that index, the distance from this to L is at most epsilon, which we chose to be 1. So, but by definition of the absolute value, we have something else. By the definition of absolute value, this implies n greater than or equal to capital N, maybe not this implies, but by the definition of absolute value, we have n greater than capital N implies -1 less than a over n divided by b over n minus L is at most 1, which implies that a over n, a sub n over b sub n is less than L plus 1, which implies that a sub n is less than L plus 1 times b sub n. And since a sub n is greater than 0, we have also that 0 is less than a sub n, which is at most this. So now we're going to use the direct comparison test. So by the direct comparison test, so n equals 1 to infinity. So like this is our term, right? This is our term that's greater than that term. But that's just a constant number. We can factor that out. So if this converges, then the sum with those terms must also converge. And that's pretty much it. So if that converges and that converges, and the contrapositive is if that converges, then that must converge. Yeah. That's the proof of the limit comparison. Okay, so I have an example somewhere I could use maybe. Okay. Let's say, what's a good example? So I guess we'll just use this one or something. I don't know. Let's see. And then we have root n all over n squared plus 1. All right, so we need to determine if this thing converges. Well, I know by direct comparison, this thing is easy. The terms here satisfy the following. So 1/2 minus 2 equals minus 3/2. All right. Now, oh, do we even need to use the direct comparison or the limit comparison test here? We don't, do we? Let me just put back to P series. Yeah. And we don't even need the limit comparison test here, right? Because I know that 0 is less than root n all over n squared plus 1, which is less than 1 over n to the 3/2. And I know that the sum of n is equal 1. Yeah. To infinity, 1 over n to the 3/2 converges as a p series with p equal to 3/2, which is greater than 1. Yeah, 2 goes into that 1 with like a little bit left over, right? I wonder why they had that example in the textbook. What was so like, am I doing something wrong? Let me see. I feel like I might have just like had a brain fart because that, yeah, the p is greater than 1 if p series. Oh, wait a minute. Yeah, no, it's done. Yeah, I don't know why they use that. In fact, I think many times you can actually disregard the limit comparison test and just use the direct comparison test. So it's not done yet, it's just like converges that. So by direct comparison tests, that is also converge. All right, so from section 9.4, oh no, yeah, 9.4. Um, 5 through 33. All right. And next time, or next lecture will be alternating series.